This presentation is to help you get started using TOLCAP. It guides you through the steps of an analysis and tries to give you the sense of the questions you need to address to get a process capability prediction. An introductory presentation addressed why you would use TOLCAP. This one explains how, but first, when do you use TOLCAP? If you're a designer, use TOLCAP from the very earliest stages of the concept design. You are probably sketching out some fundamentally important features, and these elements will doubtless give rise to certain key dimensions where the required tolerance is not negotiable. You don't need a formal engineering drawing to know this. So at this point, and thereafter whenever you are about to specify a tolerance for a vital dimension on a part, use TOLCAP and check for process capability before you get stuck with a design with problems. If you are maybe a quality engineer and you want to check why a problem feature is proving difficult to make, does the problem go back to the design? Use TOLCAP to see if there is likely to be a process capability issue. So how does TOLCAP work? The process capability of a tolerance dimension depends on the final manufacturing process to be used to determine that dimension. It also depends on the material and geometry of the part, the state of the tools and machinery, and the capability and maybe the past experience of the supplier. It sounds a complex interaction, and it is, but TOLCAP leads you through the main factors to a good working estimate of process capability. The prime factor determining process capability is the manufacturing process. Parts are formed by such process families as forming. Forging, for example, is hitting parts with a hammer to deform them plastically into shape. Machining. Turning is cutting pieces of swarf away from a rotating bar. Casting or moulding involves melting the material, pouring it into a mould and letting it refreeze. The point is that these processes essentially come down to physics, and the process capability that is ultimately achievable depends on how well an experienced manufacturer can control all the variables to get the best out of the basic physics of the process. So, how do you access and use TOLCAP? Either you will need to be a nominated user on your organisation's account, or sign up for an account on our website. Your username will be your business email, and you can set your password by following the Forgotten Your Login Details link on our login page. You could also register for your account from that page. Logging in will take you to the TOLCAP dashboard, shown here as you would see it on a desktop or laptop. But here it is again, as it might look on your mobile phone. Select New Calculation to find the predicted process capability of the tolerance you're interested in. Suppose the manufacturing process that finally determines the dimension on the part is turning or boring. Drop down the process category list and select Machining. Drop down the list of processes. You'll see there are quite a few, and select Turning and Boring. Alternatively, you could have followed the link to the list of processes and selected Turning and Boring from there. As you've seen, TOLCAP works on a computer or a mobile phone, and it works on a tablet too. And the screenshots from here on in will be as they would appear on a tablet device. Okay, so in the calculation panel, enter the dimension and tolerance of interest. In this case, 100 millimeters plus or minus 0.035. Do it in that format, even if the drawing says 100 millimeters minus 0 plus 0.07, because TOLCAP does expect a plus and minus balanced tolerance. Next, click Calculate CPK and ppm. You will see the predicted CPK, 2.35, and the equivalent defect rate, which is less than 0.1 parts per million. Next, select the Map tab and see the result on a process map. TOLCAP incorporates capability maps for more than 80 manufacturing processes. The maps plot dimension against specified tolerance for each process on a log-log scale. The diagonal lines on the maps are lines or sometimes contours of constant process capability. The higher up the map, the higher the process capability. The orange crosshairs show your calculation as a point on the map. So far, the process capability estimate is for the best a competent supplier should achieve in the ideal case. But just thinking again about the physics of the process, the properties of the material being processed will have an effect. Its hardness, malleability, thermal expansion coefficient, and so forth. Where there is a strong interaction between the process and the part material, TOLCAP provides alternative process maps for groups of common materials. The slide shows that there are separate maps for cold drawing copper alloys and for cold drawing steels. For other processes, for example for turning and boring, we selected here, the prediction from the standard map is modified by a factor dependent on the material of the part. The choices appear at the initial process selection step we went through earlier. Maybe sometime you could click on the View All Processes link to see which processes are material specific and which ones require a material factor. Anyway, for turning and boring, you will see in the calculation pane a default best case material for the process. In this case, non-ferrous aluminium alloy. Click the drop-down arrow and then select the material for this example mild steel part. Note you don't need the precise specification of the material, and should your material not be shown, you can select one with similar relevant properties. Click Calculate CPK and ppm and notice the decrease in the predicted CPK to 1.95 and that the orange crosshairs have moved down the map. But so far the result is still quite acceptable. But there are other factors that may affect the process capability for our part. First, let's consider those loosely connected with the geometry of the part. Click the Geometry wizard. And we are presented with several questions, and these may vary with the process we selected. First, we are asked how many planes we are machining at one time. We might have been facing the part while boring the hole in it. Next, is the part long and slender? Because that was much more difficult to hold tolerances than for a squat sturdy part. Let's suppose the part is long and slender, and so we select answer B. Does the part have repetitive features? Well, this would be applicable to such processes as gear hobbing, and here it could be relevant if we were turning a series of grooves which we wanted to be identical. Are there extra setup operations? Suppose we have to turn our part around to bore this feature, so we drop down the arrow, select one extra process and then click Apply. And we see the effect of the slenderness of the part and of turning it round is to reduce our process capability prediction to 1.51. Note the wand shows that we have applied the wizard, and the updated results pane takes this into account with a summary of the factors we selected. On the Map tab, we see the crosshairs show the prediction has again moved down the map towards the green capability threshold. And there are some additional variation factors yet to consider. Click the Variation wizard, and we're presented with yet more questions. Question 1, we would hope the manufacturing machinery is up to date and well maintained. The feature geometry may be at the limits of feasibility, or the part may be at the limits of size or weight, too big or too small. Let's suppose that our part is not only slender, it's long, so it's large, near the capacity limit of the lathe. So we answer yes to the component size question, and then we click Apply. And notice that CPK has fallen to 0.97 and the crosshairs on the map have turned red. Well, that's a tear up then. Maybe, but not yet. Okay, we're predicting a low CPK, but we know the factors that cause that low value. The part is big and it's long and thin. Let's take the result to the supplier and discuss the problem first. Okay, the part is near machine capacity. Is that a real problem? Does it matter? Is there a similar sized part in production? The part is long, but can it be propped in the middle or maybe held in some sort of collet so that the part is supported and the problem eliminated? Positive answers here, backed up with data from the process on similar parts, will allow us to go back to the analysis and get a better prediction. So it will be useful to save your calculation so you can share it and modify it when you've perhaps reassessed the answers you gave to the various questions or modified the tolerance. You'll be prompted to type in some reference to identify and retrieve it. You can print the saved data in the format shown or export it as a .csv row to add to a spreadsheet. This presentation hopefully leaves you ready and confident you can start using TOLCAP. If you're still puzzled, try using TOLCAP anyway. It may make sense. Or go through this material again, or see the next presentation that gives some more explanations and an alternative, simpler approach to process capability prediction. To sign up for a TOLCAP trial account, or for more information, please visit our website at www.tolcap.com.